Hello and welcome to another video on orbital mechanics. This video is another theory video and it is on the circular restricted three-body problem. This is quite an important part of the book and it's section 2.12 and it deals with having three bodies, but one of those bodies has a negligible mass compared to the other two, and this allows us to do some analysis. As you may know, a standard three-body problem is essentially unsolvable analytically, but there are some simplified versions that we can do quite a bit of work with and get some useful equations out of. So I've drawn a little diagram here, and it's a little bit different to the diagram in the book. The diagram in the book is presented more in a 3D space. You should have a look at it on page 117. But what I have here is the M1, which is the larger of the three masses, M2, which is a little bit smaller, and then the spacecraft, which has negligible mass. And we have the angular velocity of the system is going clockwise, and this is the center of gravity. And the spacecraft here is going clockwise around M1. So it's actually an orbit of M1. This is what I'm imagining for my scenario. Now, if M1 was very far away from both of these, you would imagine that it's actually orbiting essentially both of them. But I think that's more of an anomaly. It's always essentially orbiting the center of gravity that it experiences. Now, it is closer to M1, so it's going to be orbiting M1. But if it was closer to M2, or close enough to M2, it would be orbiting M2. But irrelevant, from this position, if you, and this frame here is going to stick, is going to stay in, it's a rotating frame. So we're not actually going to see these things moving in this frame. They're going to stay static. But relative to this frame that isn't changing, the velocity of M, the relative velocity is this way, roughly, and the relative movement of G is going to be this way. So this is our radius, and then coming out of the page, or sorry, going into the page in this case, because of it's clockwise. Going into the page, we have the angular velocity vector. And using our right-hand rule, we get a vector coming this way for velocity. So if we are from the perspective of M, the center of gravity is actually going this way. And from the perspective of the center of gravity, our spacecraft is going to be going this way. And the same for this planet. From the perspective of the center of gravity, the planet is going to be going this way. And from the perspective of the planet, the center of gravity will be going this way. Right? So the equation which kind of governs this is this, which is the velocity equals the velocity of the frame, which is from this point, which is actually 0 in this case, plus the angular velocity cross product the radius. So the angular velocity vector cross product the radius vector, plus our relative velocity. This is the velocity of the spacecraft. And this is the absolute. So this is, from absolute 0 of our inertial frame. So I think it's quite difficult to imagine why this is right, but if you imagine you're locked in the gravity of this, you are moving relative to this, right? And you're always going to be locked into the gravity somehow, right? So being further away doesn't change that. It just simplifies it when you imagine you're actually orbiting this. And obviously when you come around, you're going to get pulled by this. So you're probably going to be, periapsis will be this side and the apoapsis will be this side, because you're obviously getting pulled out. And in that way, it's like a tidal force. And then, so that's just, we need to know that, because later on I'll show you that implies the acceleration, 5-term acceleration formula. However, let's go back to the basics, and what we want to do, we want to derive some terms to represent R1 and R2. And we do that by saying m1x1 plus m2x2 equals 0, and that's our mass formula centered at G. And then x2 equals x1 plus R12. And from that knowledge and just general, logic, we can derive that we have a couple of constants. So these in the book, these are called pi1 and pi2. Not sure why they use those terms, but m1 over m1 plus 2 and m2 over m1 plus m2 goes here and here. If you work these out manually, you will get x1 equals m2 over m1 plus m2 r12 and x2 equals m1 over m1 plus m2. It's a bit fiddly, but you do come out with that. And then if you just plug those into the vector format, it just looks like this, right? And then R is just that. And these are all in the moving frame. I, J, and K. Well, I and J are moving vectors. K is not in this case. Well, unless the entire system is moving, K is not moving. Then, so from this vector velocity equation, we can say that the acceleration equation holds true. Now, if you want to know more about that, you should check out my video, Relative Velocity and Acceleration, linked in this video. That will explain how we get to that. In this situation, the acceleration of g is 0 here, and the angular acceleration is also 0 because it's constant, right? So we can get rid of those, and we're left with just angular velocity cross the radius plus 2 angular velocity cross velocity relative plus acceleration relative, and also this is equal to this here is in the direction into the page, and that is k, and it's k times the magnitude of that. So we're going to replace that with that, which is there, and we're going to do all the cross multiplies out. This is an absolute bugger, and I didn't do this. This is just in the book. But if you really want to go through and painfully work this out term for term, be my guest. But I didn't. I just accepted the book is correct, and when you simplify that down, you get R, the acceleration, really, R derivative, the acceleration of our spacecraft equals the acceleration of x minus 2 angular velocity, the velocity of y minus angular velocity squared times x times our unit vector I, which is moving, and then acceleration of y plus 2 angular velocity times the acceleration of x minus angular velocity squared times y on the j vector plus the acceleration of z and the k vector. So that, very difficult to accept where this is coming from, but this is essentially just taking this, our acceleration of vector or velocity equation, taking the derivative, and that works out to be this, and I explained that in another video, and then simplifying that term by term produces this. And we can also, and then, so that's the acceleration in one format. We also have it in another format, based on forces, F equals ma. And if you go to page 59 in the book, and we've covered this in other videos, you can see that the force is equal to the gravitational equations added together, and the mass of the spacecraft cancels out. So you end up with just mu1, which is the gravitational constant for m1, divided by r1 cubed times the vector r1 plus the gravitational constant of m2 divided by magnitude of r2 cubed times the vector r2, and that gives you that. And when we put those when we do those out per term. So ijk here, and then we can take the x's out of here and the x's out of here, and well, sorry, the I component here. So this is I, j, k. So we take those out and we equate them, group them up, add them together, and we get these three equations. And they are the circular restricted three-body equations. We're going to go on to Lagrange points and how we can use these equations to calculate our Lagrange points. But that is effectively the circular restricted three-body problem, mathematics broken down. If you have any questions or you think I've made a mistake, and also actually these have negatives in the book, but I looked forward and it looks like those negatives cancel, so I just left them as positive. Negative here, negative there. It didn't seem to make a difference. I think the acceleration just comes out negative or positive based on whether it's negative or positive. So that's not really relevant. It doesn't matter if it's negative or positive. I've left them as positive because I think it's simpler, and just to see if it works. But if it doesn't work, we're going to change these to negatives. But I think it will work out. It's like I say, this one took me a couple of hours to figure out how to explain it. I don't know if I've done a great job. I struggled with the concept of the relative velocity in this space, but I think I'm happy with it now. If you're still struggling to understand why this works, let me know in the comments. Like if you think I've made a mistake, let me know as well. And thank you. Goodbye.